Hi guys, welcome to another lecture in the series of Medicinal Chemistry 1. Today we'll be talking about CNS depressants, that is sedatives, hypnotics, and anxiolytics. And of course, my name is April Johnson. Alright, for these sedatives, hypnotics, and anxiolytics, they often have the same general features and they generally share at least one mode of action, and that is the positive modulation of the action of gamma aminobutyric acid, and we say GABA for short, at GABA A receptor complex. Now we have, in comparison to the other classes of compounds that we have looked at, the list of anxiolytic, sedative, and hypnotic drugs is actually very short. We're talking about benzodiazepines, Z-drugs, barbiturates, and a miscellaneous group. Now, just to mention that our focus will be on benzodiazepines, right? Just to break down the name gamma aminobutyric acid, this is the structure of GABA. So the position 1 is that of the carbon of the carboxylic acid, and so the neighboring carbon would be the alpha, then beta, then gamma, and so we have an amino group attached to the gamma carbon, and of course it's butyric acid because we have 1, 2, 3, 4 carbons, right? So that is GABA. All right, so GABA A receptor modulators. Well, benzodiazepines, and I said that will be our focus, are highly effective anxiolytic and hypnotic agents. So as we see here with the suffix zepam, so we see a lot of zepams. You might be familiar with diazepam, and in the Valium diazepam, and they bind to benzodiazepine binding site on GABA A receptor, also known as the benzodiazepine receptor, right? So this is in pink here. We have an image or a diagram of what a receptor might look like, and we see here that on the gamma subunit you have the binding of the benzodiazepine to the benzodiazepine binding site. So they are sometimes called benzodiazepine receptor agonist. So for the GABA A receptors benzodiazepine, the GABA system is important in the pathophysiology of anxiety and insomnia, right? So GABA is the most, and if you're wondering what is GABA, what does it do? It's the most common and major inhibitory neurotransmitter, NT for short, in the brain, right? And it exerts its rapid inhibitory action mostly through GABA receptors, as we just saw on the previous slide. So it is known to activate two types of receptors, that is the ionotropic GABA A and GABA C receptors, as well as the metabotropic GABA B receptor. Now, the major difference between the ionotropic and the metabotropic is that one is directly linked to the ion channel, which we saw here, directly linked to the ion channel, while the other is not. The metabotropic and is not directly linked to the ion channel. All right, so GABA A receptor is therefore the target for many of these anxiolytics and sedatives and hypnotics, and we have the benzodiazepines, the barbiturates, the steroids, anticonvulsive agents, and many other drugs that bind to the GABA A receptor in neuronal membranes in the CNS. All right, so let's look at the mode of action. So it is a ligand gated chloride ion channel, that is this receptor here. Upon activation, the chloride ion, there's a chloride ion influx and it's increased, and the membrane becomes hyperpolarized, resulting in neuronal inhibition, right? So here we have the chloride ions in the synaptic cleft, and once the ion channel opens after activation, then the chloride ion is now moved to the cytoplasm, and therefore you have hyperpolarization of the membrane. So let's look at the structure of these receptors, right? So we call this a pentameric GABA receptor. And the most common pentameric GABA receptor combination includes 2 alpha 1, 2 beta 2, and 1 gamma 2 subunit. So there are definitely other combinations. So here we have the cross section of the pentameric GABA receptor. So we have 2 alpha 1 subunits, we have 2 beta 2 subunits, and we have 1 gamma 2 subunits, right? And here we can see our GABA site and our benzodiazepine site, as well as our chloride pore, where, you know, once the channel opens, the chloride, there's an influx of chloride. And this is showing the side view, right, where you have other binding sites, right? So you have the barbiturates have a particular binding site. General anesthetics, they have a particular binding site. Other drugs, right? Ethanol, for example, would have a different binding site, okay? So this leads us now to the mechanism of action, right? So I'm going to read. When benzodiazepines bind to a benzodiazepine recognition site, as we just saw on this slide here, the benzodiazepine recognition site here, one of the several allosteric sites that modulate the effect of GABA binding to GABA A receptors located on GABA receptor complex. So the benzodiazepine, they induce conformational changes in the GABA binding site, therefore increasing the affinity of the receptor for GABA. So once the benzodiazepine binds to the receptor, it increases the affinity of the receptor for GABA. And so the frequency of chloride channel openings is increased, and, you know, clearly the chloride is going in over that resulting from the binding of the GABA alone. And the cell is further hyperpolarized because of the influx of the chloride ion, yielding a more pronounced decrease in cellular excitability. So that is the calming effect. So the benzodiazepines appear to have no direct effect on the GABA A complex or ionophore, right? Meaning it's not because the benzodiazepine bind to the receptor while the channel opens. It binds the receptor, that doesn't cause the channel to open, the ion channel to open. It's because it binds, then it increases the affinity of GABA binding, and because GABA binds, then you have an influx of the chloride ion. So yes, it's important, but it doesn't appear to have any direct effect on the GABA complex. All right, so that leads us to question 4, which is what is GABA, and draw the structure of GABA. So the answer is that GABA is the most common and major inhibitory neurotransmitter in the brain, as we said before. Its primary role is reducing neuronal excitability throughout the nervous system. So when GABA actually attaches to the GABA receptor, as we just saw, it produces a calming effect. This can help with feelings of anxiety, stress, and fear. All right, so I'm not saying that you should take any benzodiazepines right now, right, to deal with your stress. All right, so what is the structure of GABA? Was the other question? So we have a gamma aminobutyric acid. So the carboxylic acid would be at position 1, and then the alpha, this would be the alpha carbon, beta carbon, gamma carbon, and the amino group is attached to the gamma carbon, and it's butyric acid, as we said before, because you have 1, 2, 3, 4 carbons. So that is GABA, the structure of GABA. Our follow-up question 4 is discuss the mechanism of action of benzodiazepines. So what is their mechanism of action in your own words? All right, so now we're going to look at the general structure and structure-activity relationships of benzodiazepines. So this is a general structure. We have a ring A, a ring B, and a ring C. And you have some electronegative group attached to position 7 here. You have some R group attached to position 1. So that is the general structure. So now we're going to go into the structure activity relationships, and these are the things that are to the sides, right? Yeah. All right, so let's start with ring A, right, which is this aromatic ring here. Aromatic or heteroatomic ring A is required for the activity that may participate in stacking with aromatic amino acid residues of the receptor, right? So we need to have an aromatic ring or a heteroaromatic ring. So that means that one of the hydrogens, for example, could be substituted with a nitrogen, for example, right? And that would make it a heteroaromatic ring. So whether it's aromatic or heteroaromatic, it should have the ability to stack with aromatic amino acid residues of the receptor. So it's required for activity. So on ring A, as we see, we have an occupied position here, position 7, right? Or substituted position. So an electronegative substituent at position 7 is required for activity. And the more electronegative it is, the higher the activity, right? So if you get a structure, or if you're to compare various structures and there's a difference in electronegativity, which means therefore that we need to have an idea of the functional groups that are electronegative and their relative electronegativity, you know, whether one is higher or lower, and to be able to assess perhaps whether or not one is more potent than the other. But the point here is that an electronegative substituent at position 7 is required for activity, and the more electronegativity is, the higher the activity. So the more electronegative, the higher the activity. Positions 6, 8, and 9, however, should not be substituted. So 6, 8, and 9 should have no substitution. All right, so let's move on to ring C, which is here, right? And it's attached to position 5. So a phenyl ring C at position 5 promotes activity. So if the phenyl group is ortho, or that is singly substituted at this position, or doubly substituted at positions 2' and 6', with electron withdrawing group. So that's important, not just substituted, but it has to be an electron withdrawing group or groups. The activity is increased. On the other hand, if you have a para substituent, that decreases the activity greatly. So here, this position 5 substitution promotes activity. If we have substitution at 2' alone, or 2' and 6', that with an electron withdrawing group, activity is released. If we have a para substitution, that decreases the activity greatly. So for ring B, which is our diazepine ring B here, saturation of the 4-5 double bond, that is a conversion, hydrogenation, or making it a single bond, the carbon nitrogen bond, making it a single bond, or a shift of it to the 3-4 position decreases activity. So whether you have a single bond between the carbon and the nitrogen, or if you move the double bond to the 3-4, activity cut. So the alkyl substitution at position 3 decreases activity. So if you have an alkyl group like a methyl, ethyl, etc., activity decreased. Substitution with hydroxyl, however, does not. It doesn't decrease the activity. But the point here is that the presence or absence of the 3-hydroxyl group is important pharmacokinetically, which we're going to discuss right now, right? So on this side, we're saying if you hydrogenate and get a single bond, decrease activity. If you move the double bond to here, decrease activity. Alkyl substitution here, decrease activity. If you have a hydroxyl group, it affects it pharmacokinetically, right? And so compounds without the 3-hydroxyl, that's here, are non-polar, and they're also 3-hydroxylated in the liver slowly to the active 3-hydroxyl metabolites, and have long overall half-lives, right? So that's what we're saying about the compounds without the 3-hydroxyl group, right? They are non-polar, and when they are metabolized, they actually are hydroxylated in the liver, and that hydroxylated compound is also active. And so that therefore they have a long overall half-life. In contrast, if you have the 3-hydroxyl group here, they're much more polar for obvious reasons, rapidly converted to the inactive 3-glucuronides, which are excreted in the urine and are thus short-lived, right? So that is the difference between the one with the hydroxyl group and the one without, with and without the hydroxyl group. All right, so for the 2-carbonyl function, and we're still on the diazepine ring B, so we spoke about 3, 4, and 5. So at position 2, we have a carbonyl function, and that is important for activity, as is the nitrogen atom at position 1. So if we have a N1 alkyl side chain, they are tolerated. So what the carbonyl actually acts as is a proton acceptor. So a proton accepting group at C2 is required and may interact with the histidine residue, which is a proton donor in the benzodiazepine binding site of the GABA receptor. So again, it's all about how the molecule or how the drug interacts with the receptor, right? So if we have a proton acceptor interacting with a proton donor on the receptor, that is perfect for the activity. So you could also have a triazole and or a imidazole ring instead of, the substitution here, instead of the carbonyl and the R group here. We could have those group that are capable of hydrogen bonding and also increase activity. So that's an activity that you could try to replace these the carbonyl and the R group here with a fused triazole or imidazole ring at 1 2 here, and that will increase the activity. All right, so this is a summary of everything that I just said. Everything related to ring A, ring B, and ring C. The effect of aromatic ring, heteroaromatic ring. The aromatic ring might have a little activity over the heteroaromatic ring. We need the electron withdrawing group to increase the activity. We need a phenyl group to increase the activity at position 5. It may or may not be substituted at positions 2' or 6'. The para substitution decreases the activity, or hydroxyl group. So when you're looking at this, the double/ mean with 3 hydroxyl group. Double/O means without 3 hydroxyl group. So substitution with a 3 hydroxyl group and the activity. So with the hydroxyl group, polar readily excreted decreases duration of action. Without nonpolar, hepatic oxidation to the hydroxyl and which is an active metabolite, and therefore it increases the duration of action. We mentioned the importance of the carbonyl group as a hydrogen accepting group, which increases the activity, and we could also have a fused triazole or imidazole ring, which would increase activity. So fused to position 1 2 here. So we're going to look at just 2 drugs within this class of compounds, right? So the first one is Chlorides epoxide, and in the field of benzodiazepine, it was opened with the synthesis of Chlorides epoxide by Sternbach. And it was Randall who discovered its unique pharmacological properties. So here we see that we have the phenyl group unsubstituted at position 5. We have an N-oxide, and we don't have a carbonyl here, but we have an amine bonded to a methyl. We have a double bond here between the carbon and the nitrogen, and of course we have our electron withdrawing group at position 7, and position 6, 8, and 9 are unsubstituted. All right, so let's look at the details of this drug. So this is the actual chemical name, and it's well absorbed after oral administration. Peak plasma levels are reached in 2 to 4 hours. The half-life is 6 to 30 hours, which is a long time. And the metabolism is N-demethylation. So you cut off the methyl here, and hydrolysis of the condensed amidino group, which we're going to see in a little bit, the structure of the moxepam as a major metabolite. So because of the long half-life of the parent drug, which is 6 to 30 hours, and the fact that it produces active metabolites, this drug is very long-acting and self-tapering, right? And as with diazepam, repeated administration of Chlorides epoxide can result in accumulation of parent drug and its active metabolites, and thus cause excessive sedation. And everything I just said will become clear, or hopefully will become clear once you see this. All right, so as we said, the half-life of chlorides epoxide is 6 to 30 hours, right? This is chlorides epoxide here. And this is the route of how it is metabolized and eliminated, right? And the first step, as we said, is the N-demethylation to an active metabolite, right? And then it is, the hydrolysis results in the formation of the demoxepam, which is also active, right? So here we have lost the nitrogen, and now it's a carbonyl group here and in the demoxepam, right? And then moving, so the demoxepam is also active, right? Moving from there to nordiazepam, what happens there? Okay, well, we lose the oxide, and this metabolite is also active. And look at the half-life, 40 to 50 hours, right? And then going from nordiazepam to oxazepam, which is also active and has a half-life of 6 to 12 hours, right? The difference between here and here is that it is hydroxylated. So remember what we said about the compounds that are not hydroxylated? Eventually in their metabolism, they do get hydroxylated and then conjugated and eliminated. So the conjugation is glucuronidation and it's excreted, right? So this should make this point clearer. It has a long shelf life, the parent drug, and it has active metabolites, and this should make sense now that it's long active, and with repeated administration, the drug as well as its metabolites can cause excessive sedation, and this should be clear here, right? Starting here, all of the intermediates are active, or all of the metabolites, I should say, are active, and in some cases have very long half-lives before they are actually excreted. So let's look at diazepam, which was also in that diagram, but we're going to speak on it when in the next slide. All right. So diazepam is a prototypical benzodiazepine and was the first member of the benzodiazepine 2-on group to be introduced, right? So here, let's look at chlorides epoxide, right? So we don't have a carbonyl here. While for diazepam, we do have a carbonyl at position 2, and it was the first one with the 2-carbonyl to be introduced. It's very lipophilic and is thus rapidly and completely absorbed after oral administration. The maximum peak blood concentration occurs in 2 hours, and elimination is slow, as with the chlor epoxide that we saw earlier, and with a half-life of about, look at that, 46 hours. That is significant. That's a very long time. And just in case you don't remember what half-life is, that is the time it takes for it to reach half the concentration. So 46 hours is only half the concentration at that time. So as with chlordiazepoxide, which if I didn't say, this is what I should have said, chlordiazepoxide, diazepam is metabolized by N-demethylation as well. So we have a nitrogen group here, and we have a tertiary amine, which can lose the methyl group in the metabolism. It is also 3-hydroxylated to the active oxazepam, and then metabolized according to the general scheme that we saw earlier, and we're going to look at after this. All right, so like chlorides epoxide, repeated administration of diazepam leads to accumulation of an active diazepam, which can be detected in the blood for more than 1 week after discontinuation of the drug, right? So half-life of diazepam is 46 hours. So let's look at the metabolism. So it's just a fraction of the image that we saw earlier, because it only has the diazepam, which has a half-life of 46 hours. And as we said, it's demethylated, N-demethylated here to nordiazepam, which is also active and has a half-life of 40 to 50 hours. This is a long time, guys. And then the very slow oxidation, so the 3 position here form the hydroxyl group, oxazepam, which is also active and has a half-life of 6 to 12 hours, and then it is conjugated and excreted, right? So clearly it shares a similar pathway to chloride epoxide, which we saw here, right? So we have the common metabolites of benzodiazepines here, right? So as with chlorides epoxide, we end up with nordiazepam and oxazepam as well. All right, so this drug is long acting, as we have seen. It is metabolized as we have seen as well by these CYP enzymes, because the clearance is decreased in the elderly and in patients with hepatic insufficiency. A dosage reduction may be warranted. So it's widely used for several anxiety states and has an additional wide range of uses, such as anticonvulsant, pre-medication in anesthesiology, and various spastic disorders. All right, so our final question is, discuss the activity of the proposed drug below. So this is my designer drug, right? So looking at the structure, tell me your proposed, what do you think that would it be active? Let me know. All right. So if you answered maybe, well, let's look at it in more details. So this is the general structure, and I have it here because of the numbering. So this is my designer drug, and this is the answer. So carbonyl group at position 2 is an hydrogen accepting group, which increases activity, right? So we have that. We have a methyl on the nitrogen at position 1, and that should give it optimal activity. We have a hydroxyl group at position 3, so it's polar, therefore, and it's readily converted to the excreted glucuronide, and that therefore decreases the duration of action. So my drug might be active, but it has a short duration of action because of the hydroxyl group at position 3. Now we also have a 5-phenyl group here, position 5, and that increases activity. We have a heteroatomic ring A here, and it may have a lower activity than the aromatic ring, but still active nevertheless. And then at position 7, we have a bromine, and it's an electron withdrawing group, and clearly bromine is electronegative, which increases the activity, right? So we're saying here that we expect this drug to be active but it will have a short or decreased duration of action because of the 3-hydroxyl group here. All right. So our final follow-up question is, design your own anxiolytic sedative hypnotic drug and comment on its activity. All right. So if you made it to the end, thank you so much for watching, and see you next time.